All right, so if the current is what, dq dt, then that would be what, ddt of q e to the negative t over rc, which would be what, q e to the negative t over rc times what, negative 1 over rc. Did I do that correctly? All right, so that would be what? Negative q over rc e to the negative t over rc? Yes. Unit-wise, is this okay? What is q equal to? If q is equal to what? CV? So I'd have CV over RC. So do my units make sense? Yeah. Okay. Now, what does this negative sign right here represent? That will come through this function right here, but this negative sign right here indicates that the current through the resistor is in the opposite direction than when the capacitor isn't in the circuit. I mean, when the capacitor is discharging later. So this means the current has changed direction. So it's okay that there's a negative sign there. Now let's look at the graph and let's look at what happens at the time constant. So if the current, we look at it at tau, which is RC, that would be negative Q over RC, e to the negative RC over RC, which would be what, negative Q over RC times 0.36, right, e to the negative 1. And if Q is CV, so negative C, and then I'm just going to write V. V of the capacitor over RC. Then at one time constant, what's our current? Let's look at the absolute value graph though. The negative sign just refers to the direction of the current, that it's flipped over. Not that necessarily it's going down, it just means it's flipped. And I'll show you an example of how we could see that flip in just a second. So what's our current going to start out as? Well, e to the 0 is 1, so we're going to start out at whatever the voltage over the capacitor divided by the resistor is. And then what does e to the negative x look like? Same old dying exponential decay looking thing right there. And so at one time constant, tau, again, we're at what, 36% of our original current? 36% of I naught. So now let me give you an example of when you would see the direction change. Okay, so a circuit could be wired up like this, and this will be similar to what we do in our little lab. So here is a EMF, and there's a switch here. Then we're going to have a resistor and a capacitor. And then I'm just going to have a wire out over here. Nothing going on over here. Okay. So initially, if the capacitor is just sitting here and it's not charged, the resistor is just sitting here, no current's running through it, the battery is just hanging out, If we close this switch, there will be a current run through, or current run through the resistor. Doesn't run through the capacitor because capacitors don't let charge flow through, but the capacitor will build up its charge. So then it will be totally charged up big Q. Okay, so once it gets completely charged, the current in the resistor is 0. So initially, the current through the resistor was this way. Okay, that was what our I naught would have been, our initial current when it was charging. Now, this top side of my capacitor becomes positively charged. The bottom side of the capacitor becomes negatively charged because the top side of my capacitor is connected to the positive side of the battery and the negative side is connected to the bottom side. That's how you can tell what charge goes where. So then if I open this, there's no flow happening here, and I close this guy right there, what's the charge on the capacitor going to do? It's going to move, okay? And it's going to move in the direction that your positive test charge would move, the conventional current. So positive charge carriers, whatever you want to describe them, would run this way. So we get a current like that. So now which way is the current through the capacitor when it's discharging? Is it in the same direction or the opposite direction? The opposite direction. So that'll give you an idea of why that negative sign was there. It just means it's flipped from what it was. It does not mean it's down. It does not mean it's left. It just means it's flipped from the charging direction. Okay? Here we go. So if we have this situation where we've got the capacitor, we have the 10-volt battery, blah, 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 and we're trying to find the resistance. We've got the 4 volts in 3 seconds. Let's look at the Q of T equation. Q of T was equal to what? The capacitance times the EMF times 1 minus e to the negative t over RC. Right? Okay. So how can we get voltage from that? Doesn't Q equal CV? So could we write this as the voltage of the capacitor as a function of time is equal to the EMF of the battery, 1 minus e to the negative t over RC? Yeah? Do we have the voltage at a particular time? We got 4 volts is equal to 10. 1 minus e to the negative what? 3 over R times C. You know what I'm going to do? I'm going to leave it as RC. Let's solve for RC and then we'll solve for R, because then I don't have to write a tiny little 10 to the negative 6 in that little tiny denominator. Is that okay? All right. So then we have what? 4 tenths is equal to 1 minus e to the negative 3 over RC. So 4 tenths minus 10 tenths, how about that? Is equal to negative e to the negative 3 over RC. So what's that? Negative 6 tenths is equal to negative e to the negative 3 over RC. So boop, boop. How about that? So that how do we get rid of that E business? Oh, we do the ln. So is that the ln of what? 0.6 is equal to negative 3 over RC. So RC is equal to negative 3 over the ln of 0.6. Okay, so now that is what RC is equal to. So then R would be equal to 5.87 divided by 10 times 10 to the negative 6. Is that right? So what is our R equal? 6. Yes? 5. What? Caterpillars? Ohms. Okay.